You think rain is water, droplets condensing in clouds, falling from the sky, washing away dust. But that's just Earth. Step outside our little blue bubble and rain becomes something else entirely. Glass shards flying sideways at 5,000 miles per hour. Diamonds the size of mountains sinking through frozen oceans. Molten iron condensing into droplets. Rocks evaporating and precipitating in a never-ending cycle. These are real places. Real planets, real weather systems that would shred you in seconds. And we can prove it. Numbers that came back from space telescopes and were confirmed in laboratories here on Earth. 1020 Nature paper on WASP-76b's iron detection using espresso at the Very Large Telescope. The August 2017 Nature astronomy study from SLAC National Accelerator Laboratory, proving diamond formation under Neptune-like conditions, and the November 2020 monthly notices of the Royal Astronomical Society, paper modeling K2-141b's rock vapor cycle. Sources that come from direct spectroscopic analysis, laser experiments, and atmospheric modeling, not speculation. Now back to the information. Planetary scientist Marvin Ross publishes a theory. Deep inside Neptune and Uranus, methane molecules, one carbon atom bonded to 4 hydrogen atoms, get crushed by pressure exceeding 2 million atmospheres. Temperature hits 5,000 Kelvin. The methane breaks apart. Carbon atoms separate from hydrogen. Then they compress, crystallize, form diamonds. Solid diamonds that sink through layers of icy slush toward the rocky core. For 36 years, this remained speculation. You can't send a probe 8,000 kilometers into a gas giant. You can't measure what's happening in an environment where the pressure would flatten a submarine like a tin can. They're using the Linek coherent light source, an X-ray free electron laser that delivers pulses lasting 50 femtoseconds. A femtosecond is 1 quadrillionth of a second. Carbon atoms separate from hydrogen within nanoseconds. Siegfried Glenzer, professor of photon science at Stanford and director of SLAC's High Energy Density Sciences Division, confirmed it. We saw carbon clusters forming under the presence of hydrogen, and then we saw those carbon clusters forming diamonds under high pressure. The hydrogen stayed present during compression, critical, because that matches what happens inside Neptune. Neptune generates more than twice the energy it receives from the sun. Nobody knew why. Now there's an answer. Diamonds, forming and sinking, create friction. Friction generates heat. Heat drives atmospheric circulation. The planet's entire energy budget could be explained by diamond rain. Diamonds could reach millions of carats in weight. Some models suggest a layer of diamonds accumulates around each planet's core, a shell of compressed carbon kilometers thick. The experiment shows oxygen makes diamond formation easier. It helps separate carbon from hydrogen. The yield increases. Published in peer-reviewed journals. Diamond rain on ice giants isn't a hypothesis anymore. It's confirmed atmospheric chemistry. 0.92 times Jupiter's mass, but inflated by heat to twice Jupiter's radius. The temperature difference drives winds at 18,000 kilometers per hour. The planet passes in front of its star from our perspective. Light from the star filters through the planet's atmosphere. Different molecules absorb different wavelengths. The explanation is immediate and brutal. On the day side, iron exists as gas, individual atoms floating in atmospheres so hot that metal evaporates. Winds carry this iron vapor to the night side. Temperature drops, iron condenses, forms liquid droplets. Molten iron rain falls through the atmosphere of a planet with no surface to catch it. The iron drops sink deeper into the planet until they hit layers hot enough to vaporize them again. The cycle repeats. Iron evaporates on day, travels on supersonic winds, condenses on night, rains down, sinks, vaporizes, returns. A fraction is injected into the night side owing to planetary rotation and atmospheric winds. There it condenses and rains down. New atmospheric models using corrected data suggest the iron rain detection holds but requires updated concentration values. Stable cloud layers. If confirmed, it means despite the chaos of iron rain and 18,000 km/h winds, parts of the atmosphere maintain enough structure to create optical phenomena. No methane present, contrary to previous assumptions. The discovery provides another piece of the atmospheric chemistry puzzle: sulfur compounds, iron vapor, hydrogen, all mixing in an environment where metal literally rains from the sky. Constellation Cygnus, hot Jupiter, HAT P7b, 16 times larger than Earth, mass equivalent to Jupiter. Orbital period 2.2 days, discovered in 2008, confirmed by Kepler Space Telescope during its primary mission. Bright enough for atmospheric characterization. The hottest spot isn't directly facing the star as expected. It wanders across the day side. Why? Massive storm systems, atmospheric dynamics creating weather patterns visible from over 1,000 light years away. The temperature gradient drives an equatorial jet stream with dramatically variable wind speeds. Sapphires are corundum with titanium and iron creating blue. On HAT P7b, temperatures are high enough to vaporize aluminum oxide. The vapor forms clouds. Those clouds get caught in the jet stream. They build up, sweep across the planet, die away. The cycle repeats over timescales of tens to hundreds of days. Corundum, or perovskite, calcium titanium oxide. Corundum fits better. Aluminum is more abundant than titanium in typical planetary compositions. There's sufficient available aluminum to form optically thick clouds. Perovskite requires more specific conditions. Ruby and sapphire rain falling through an atmosphere 2,000 degrees hotter than molten lava. Previous studies caught snapshots. Armstrong's team watched the planet for 4 years, tracked cloud formation, measured brightness variations, documented how atmospheric circulation evolves. Our full understanding of these planets and the clouds in their atmospheres is just beginning. Create the variable weather that makes the planet's brightness shimmer when viewed from Earth. Surface pressure 1.45 bars. Temperature minus 179 degrees Celsius, minus 290 degrees Fahrenheit. Cold enough that water is rock-hard ice. Methane exists as liquid. Instruments measure atmospheric composition. Cameras capture pale hills, dark channels, features shaped by flowing liquids, by liquid hydrocarbons. 3 large seas near the North Pole. Kraken Mare is the largest, about 400,000 square kilometers, larger than the Caspian Sea. Ligeia Mare is second, 126,000 square kilometers. The team used Cassini's radar instrument data from flybys between 2007 and 2015. They measured thermal emission from Ligeia Mare, detected subsurface reflections, indicating depths up to 160 meters. Instead, they found methane dominance. 2 explanations. Fresh methane rainfall continuously replenishes the sea, or something removes ethane, it might sink into the seabed, form a sludge layer of organic-rich compounds. 120,000 square kilometers, half the combined surface area of the Great Lakes, the feature appears, then disappears relatively quickly. Previous observations caught rainfall in the southern hemisphere when it was summer there. Something in the models needs adjustment. The absence of clear cloud signatures before rainfall is a mystery atmospheric scientists are still investigating. Cassini observed rainfall on Titan only a few times during its 13-year mission. Rain is rare compared to Earth. The atmosphere holds methane vapor. Clouds form occasionally, but precipitation events are infrequent. When they occur, they can be massive, monsoon-like, creating temporary lakes that evaporate within days or weeks, measured by multiple instruments over more than a decade of continuous monitoring. Radius 1.5, 1 Earth radii, mass 5.08 Earth masses. Density 8.2 grams per cubic centimeter, 1.48 times Earth's density. The high density indicates massive iron core, 30 to 50% of the planet's total mass. Computer simulations modeling K2-141b's atmospheric conditions. The results describe a planet more extreme than anything previously documented. Most tidally locked planets show 50-50 day-night split. K2-141b's geometry creates asymmetric heating. Ocean of liquid rock, 100 kilometers deep. The atmosphere is rock vapor, sodium, silicon monoxide, silicon dioxide, quartz, all evaporated from the molten surface, all existing as gas. Solid chunks of silicon dioxide, sodium compounds. They fall as rain into the magma ocean on the night side. Nicholas Cowan from McGill University, co-author on the study, emphasized the instability. The return flow of the magma ocean to the day side is slow. The mineral composition will change over time, eventually changing the very surface and atmosphere of K2-141b. The atmosphere thins or thickens depending on which compounds dominate. The magma ocean's composition drifts. That makes it easier to detect with space telescopes. James Webb. Space telescope can take high-resolution spectra, confirm the predicted composition, measure atmospheric layers, test whether the model matches reality. Second planet from the Sun. Almost Earth's twin in size and mass. But there the similarities end. Surface temperature 467 degrees Celsius, 872 degrees Fahrenheit. Hotter than Mercury despite being farther from the Sun. Atmospheric pressure 93 bars, equivalent to being 900 meters underwater on Earth. Remaining 3.5% mostly nitrogen. The clouds are sulfuric acid, concentrated, pH around -1.2, the most acidic rain in the solar system. The process happens continuously in the upper atmosphere around 60 to 70 kilometers altitude. The sulfuric acid droplets fall from the clouds. They're heavy, concentrated, 70 to 99% sulfuric acid solution. As they descend, they enter hotter atmospheric layers. Around 30 kilometers altitude, 98,000 feet, the temperature reaches 300 degrees Celsius. Precipitation that evaporates mid-fall. The acid breaks down into sulfur dioxide, water vapor, and oxygen. Those gases rise, cool, recombine at altitude into sulfuric acid, form clouds again, rain down, evaporate, repeat. The surface temperature is too high for liquid to persist. The hypothesis remains contested. Ammonia detection is difficult. Concentrations would be parts per million, but if true of Venus B, it means Venus's clouds might be less hostile than assumed. Not habitable in any conventional sense, but chemically less extreme. 20% conversion within 6 hours. Driven by surface-catalyzed photoreactions on sulfur allotropes. Peak ammonia production rate, estimated at 10 to the 13th moles per year per kilometer within the sulfuric acid clouds. Documented the cycling. Winds reach 8,700 kilometers per hour, 5,400 miles per hour, among the fastest measured on any planet. Blown sideways, faster than the speed of sound. No methane present despite earlier predictions. The sulfur discovery adds another layer, sulfur compounds, glass particles, carbon monoxide, all mixing in winds that would strip flesh from bone. But the conditions are right, the chemistry is confirmed, the physics supports it. Corundum clouds swept across planets by supersonic jets, methane lakes fed by rare storms on a moon colder than Antarctica, rocks evaporating into mineral vapor and raining back down into magma oceans, sulfuric acid boiling before it hits the ground, glass shards flying horizontally at hypersonic speeds. Modeled with physics that matches reality. The sources are in peer-reviewed journals, the data is public, the experiments are repeatable. Espresso at the Very Large Telescope detected neutral iron absorption lines in WASP-76b's atmosphere during the March 2020 observation campaign. The signal was strong on the day side, absent on the night side. The interpretation is unambiguous. Iron condenses and precipitates. Photometric data showed brightness variations consistent with moving cloud formations. The only clouds that fit the temperature and pressure profile are corundum. The June 2016 observation caught rainfall in real time, 120,000 square kilometers, visible in reflected sunlight, gone within weeks. Circulation. The model is falsifiable. James Webb observations contest it. If you value documented planetary science and exoplanet research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Finding diamond rain on Neptune tells us how ice giants distribute heat. Understanding iron rain on WASP-76b reveals atmospheric chemistry on hot Jupiters. Observing corundum clouds on HAT P7b shows us how mineral aerosols affect albedo and energy balance. Studying methane rain on Titan demonstrates hydrocarbon cycles on worlds too cold for liquid water. Modeling rock rain on K2-141b gives insight into early planetary evolution. Measuring sulfuric acid rain on Venus reminds us that extreme chemistry doesn't preclude interesting processes. The methods used to study these systems extend beyond their home planets. Spectroscopy developed for Venus works on exoplanet atmospheres. Shockwave experiments designed for Neptune apply to understanding collisions in protoplanetary disks. Circulation models created for Titan inform predictions about ocean worlds around other stars. Enough to calculate size and orbital period, maybe mass if radial velocity data exists, but atmospheric characterization requires more, higher resolution spectra, longer observation campaigns, instruments sensitive enough to detect absorption lines from molecules in alien air. WASP-76b, HAT-TP-7b, K2-141b, all are targets. Webb can measure atmospheric composition layer by layer, test whether models match observation, potentially discover new types of precipitation nobody has predicted. These will have adaptive optics sharp enough to directly image some exoplanets, watch weather systems evolve in real time across alien skies. Maybe even catch diamond formation, if they sink deep enough before crushing pressure destroys them. These missions will answer questions. They'll also raise new ones, because every time we look at a planet closely, it surprises us. Before Espresso observed WASP-76b, iron rain was hypothetical. Hot Jupiters should have metal-rich atmospheres. Theory predicted vaporization and condensation. But theory isn't proof. Seeing the iron signature appear and disappear with planetary rotation proved the cycle exists. But creating the conditions in a laboratory and watching carbon compress into crystalline structures within nanoseconds turned possibility into fact. The universe is vast. We've characterized fewer than 1% of known exoplanets in detail. Most remain mysterious. Size and mass estimates, rough temperature calculations, guesses about composition. The precipitation types we've documented are almost certainly just the beginning. Carbon soot, Every combination of elements and temperatures creates different possibilities. Given the diversity of exoplanets discovered so far, the range of possible precipitation types is enormous. Hot Neptunes with water vapor that flashes to plasma, super Earths with carbon dioxide, dry ice, mini Neptunes with exotic ices forming at pressures. Earthly matter never experiences. Ground-based surveys keep pace. Every year brings dozens of new candidates, some close enough for atmospheric studies, some too far but still adding to statistics, some so strange they force us to reconsider what planetary science thought it understood. Team publishes in Nature Communications, follow-up to the 2017 SLAC experiment, this time using PT plastic with oxygen included. The experiment showed diamond formation happens faster with oxygen present, but it also showed something else. On Neptune, this process could create sheets, layers, not individual diamond droplets, but interconnected lattices descending through the icy mantle. All could be influenced by precipitation we're only beginning to understand. Diamond sheet formation explains Neptune's heat flux better than isolated droplets. The sheets create more surface area, more friction, more energy conversion. The planet radiates 2.6 times more energy than it receives from the sun. Previous models using single diamond particles couldn't account for the entire excess. Sheets can. Offset from the planet's center by 0.5 Neptune radii. Uranus has similar asymmetry. Both ice giants show magnetic fields that don't align with their cores. Diamond precipitation might be the answer. If sheets accumulate unevenly, if they create zones of different conductivity, if their descent stirs the icy mantle in complex ways, then magnetic field generation could happen in unexpected locations. Voyager 2 is the only spacecraft that visited Neptune and Uranus. August 2009 for Neptune, January 1986 for Uranus, brief flybys. Revolutionary for their time, but limited by technology 4 decades old. Flight time, 13 years. Arrival mid-2040s. The mission could directly test diamond rain theories, drop a probe into the upper atmosphere, measure composition as it descends. Include silicates, mix in nitrogen compounds. Each variation probes different chemical pathways. The shock compression techniques developed at SLAC have applications beyond planetary science, material science, fusion research, high-energy density physics. The same lasers and X-ray diagnostics used to watch diamond formation help physicists understand matter inside stars, inside fusion reactors. On Earth, the water cycle transports roughly 500,000 cubic kilometers annually. Rain distributes heat from tropics to poles, drives weather, creates climate zones, makes Earth habitable. All measurable with precise gravity mapping from an orbiter. On HAT P7b, corundum clouds affect how the planet absorbs and reflects starlight. Albedo controls temperature balance. Temperature drives circulation. Circulation moves clouds. The 4-year Kepler observations showed variability. Answering whether the atmosphere is stable or chaotic requires longer baseline observations. Decades, not years. River valleys, alluvial fans, erosion patterns, but carved by methane instead of water. Organic compounds rain down as tholins, dark material that coats the surface. Methane rain washes them into valleys, collects them in lake bottoms. Over time, this creates layers made of hydrocarbons. The building blocks of life. Titan's surface temperature is minus 179 Celsius. Too cold for biochemistry. But the chemistry happening there might be prebiotic. Make the star twice as luminous, and you get K2-141b, permanently locked in the molten stage. Same distance from the sun, same size, same mass. But Venus took a different path, lost its water early, carbon dioxide accumulated, surface temperature soared. Surface temperature rose to 467 degrees. The transformation was permanent. Different types of precipitation tell different stories. Each one is a diagnostic, a fingerprint of atmospheric conditions, temperature profiles, pressure gradients, chemical abundances, energy sources. Finding new examples tests our understanding. Can we predict what rain forms under given conditions? Can we work backward from observed precipitation to infer atmospheric structure? Not just cataloging worlds, but understanding their atmospheres, their weather, their precipitation. Because precipitation is where atmosphere meets surface, where chemistry becomes geology. Every technique adds evidence. 1029. These instruments will characterize hundreds of exoplanet atmospheres, find new precipitation types, test models. On WASP 76b as molten iron, on HAT P7b as corundum crystals, on K2-141b as vaporized stone, on Venus as acid that evaporates, on HD 189733b as glass flying sideways faster than sound. Precipitation shaping planets. And we can measure it, study it, understand it, from 200 light years away from laboratory experiments lasting nanoseconds, from computer simulations running on supercomputers. That measurement and theory combine to reveal reality.